Hello everyone, thank you for joining us for today's webinar. My name is Neil Foley and I'm the Applications Engineer here at RISE. Today we're going to be discussing component consolidation, particularly with regard to using it in manufacturing. So component consolidation is primarily a subtopic of designing for additive. So it's most useful when moving from a traditional method of manufacturing and then looking at how you may want to redesign the way that you are doing things for use with an additive technology. It's also useful if you have transferred over to an additive technology and are looking to make things a bit more efficient by reducing some of the complexity in the assembly of your components. So the most effective way of using component consolidation is to combine components of rigid assemblies. So if you have a combination of parts that are manufactured separately but then fastened together, fastened rigidly together, this could include sheet metal, it could include milled parts, but the most important thing is that it's most easy to do component consolidation if those components are fastened rigidly together. So what component consolidation can help you accomplish is by putting multiple parts into a single build, it reduces the number of builds required to create the full assembly. It also simplifies the assembly process and reduces the amount of time it takes. So by reducing the number of components from, say, 10 components down to perhaps 3 components of sub-assemblies, then you're now only assembling 3 components together instead of 10. And finally, it's able to reduce or eliminate the need for the fasteners and other external hardware that you would previously have been using to combine those components together. So some of the things that make component consolidation more easy to accomplish with additive manufacturing versus traditional manufacturing are, for one thing, the geometric limitations of these two different domains of technologies. So with additive manufacturing, you're typically able to produce much more complex surface geometries than with traditional manufacturing. This is because with traditional manufacturing, you'll normally be using flat milling tools or machining devices that create flat creases, and this makes it easy to create flat geometries or simple curves on traditionally manufactured parts, but it's much more difficult to create narrow or complex crevices or combinations of complex small pieces on a part. So one of the benefits of additive manufacturing is not only is it easier to produce these complex geometries, but it adds very little or no additional cost because it will essentially just add the amount of cost that it takes to print the one assembly rather than printing separate pieces. And finally, by printing with additive manufacturing, you are able to automate the production of the sub-assemblies that you are consolidating rather than manufacturing each piece separately and piecing it together. So now we'll look at some of the features of RISE's technology that make it particularly effective for this application. So the primary technology that RISE uses that separates us is called augmented polymer deposition, which is a patented technology where we are combining thermoplastic extrusion nozzle with the type of print heads you would find with a 2D printer. And this allows us to, between layers of extruded thermoplastic, jet different functional inks that allow us to achieve a variety of effects. So this can include marking ink, which allows you to apply text or images to the surfaces of parts. and it can also include things like what we call a release ink, which is jetted between the support and model structure of parts and makes it very easy to rapidly remove the supports from the model. Because of this release ink capability, removing supports from Rise is even easier than many other additive technologies, and that makes producing these complex geometries even more feasible. So here are some of the most useful effects of component consolidation. Again, you want to primarily focus on rigid assemblies or subassemblies, and if you have some sort of subassembly that is fastened rigidly, it may be a good candidate. So some of the best things to use it for are fixtures or jigs, and some of these can include test or inspection jigs, breadboard mounts, or CMM fixtures. Some other things that it's useful for include tooling, end-use parts, and replacement parts. So the main thing that all of these share is that they're all the final use of the part that you are producing. So if the assembly that you're creating is intended to be the final product, whether it's to be the final part that's used in your manufacturing, or if it's the final part that will be sent to a customer, then using component consolidation may be a good approach. With prototypes, however, it's a bit more tricky, because in cases where you are prototyping with additive manufacturing, but you intend to ultimately manufacture the part with another traditional method, then component consolidation can make that process even more complicated, because once completing your prototype, you'll then have to redesign it again for a traditional method of manufacturing. So if you are looking to use prototypes, then there are a few things you'll want to pay attention to. It is good for testing form, fit, and function. So one of the best places to use component consolidation with prototyping is for visual design prototypes. So that's something like this shampoo bottle shown on the right here, which has about 3 components: the main light pink bottle, then the darker purple cap at the top, and the connection between the two, the nozzle at the top. So printing this in one piece is a lot more appropriate for testing the form and fit of the bottle than if you were to print 3 separate components and combine them. But of course, you wouldn't be using additive manufacturing for the final version of this bottle, so you would not want to use this approach to design the function of the part. So when you are looking to implement component consolidation, there are just a few things you'll want to pay attention to as you get started. The most important thing is recognizing which components from your assembly can be combined. So one thing you'll want to pay attention to is the total size limitations. If you are using additive manufacturing, then you probably have some limitations on the size of the parts that you can produce. So you don't want to combine small components up to the point that they are too large to fit in your build plate. So you can see here that this part was produced as a combination of short tracks to test the, it's an inspection gauge, a go-no-go gauge to test the shape of a bent tube, and because too many parts of it have been combined, it no longer fits in the build plate. So you'd have to instead reduce this in size and print it in perhaps 2 pieces, and then combine it afterward. Another thing you'll have to pay attention to is tolerances. You'll want to make sure that the additive manufacturing method that you are using is capable of meeting the tolerances that are required for the function that you are printing the parts for. If in fact it does not, then you may want to include some more precise technologies in producing certain parts of your assembly. Another thing is internal components. If you do have internal components in your assembly with perhaps two other components that wrap around it and fasten together, then it would not be appropriate to produce those two outer components simultaneously, or else you wouldn't have a way to fit the internal component into it after the fact. So if you have internal components, you'll want to keep the parts of it that will be internalizing that component in separate build jobs. And finally is joints. So I've already mentioned that you'll want to primarily stick to rigid assemblies and sub-assemblies when consolidating components. There are a few ways of producing joints, but typically you'll want to keep joints separate, and each rigid assembly piece will be printed in one build, and then you'll combine those into a flexible full assembly after all of them have been printed. And finally, there are a few different ways of creating the consolidated component assemblies. One of them is to just take the model files in your software and combine their geometries together. And this is a pretty quick way of accomplishing what you need to. If you have some more strict requirements, then you may actually benefit from redesigning the part as a single piece, and this can help you reduce the material usage or reduce the time to print and things like that. It gives you a little more control over it, but it'll also be a bit more work starting from scratch like that. So now I'll discuss a few best practices. So one of the things you'll want to do when converting to additive from another method is, depending on the method, you'll want to pay attention to, for example, eliminating the bulk from milled parts. So in this image on the bottom, there is a part being milled that has a lot of bulk to it. Additive manufacturing is opposite, of course, of subtractive manufacturing, where in subtractive you'll start with a bulky stock piece and you'll remove material until you get the shape that you need, and you won't typically remove more material than is necessary, because that just adds to the production time and the complexity of the program. On the other hand, with additive manufacturing, you'll start with an empty build plate and build up only the portion of the geometry that you need. So if you're converting from a milled part design to an additive design, then you're likely to have a fair bit of extra bulk on the part, and it may be useful to eliminate some of that to reduce your material usage and the print time. A few other different types of traditional manufacturing technologies include sheet metal and injection components, and if working with these, it's often best to thicken the walls of those parts just to add some strength to them. Things like injection molding are often limited by the cooling process within the mold, and so they'll typically be used with thinner geometries, but additive doesn't have that same limitation, so it's best to add strength where needed. This can be done either by thickening it or using ribs or chamfers to increase the strength. Some other approaches that you can use include topology optimization if it's appropriate. This would mainly be in cases where you are really focused on reducing the print time or the material usage, but you still care about strength, and topology optimization can give you a very optimized geometry to use for the part. And as you can see in this picture at the top, it can also automate the process of consolidating your assembly components. So this is an assembly that had 3 manufactured pieces with something like 10 fasteners to hold those parts together. And by using topology optimization or even another method to combine those, you can reduce it to a single part that will just need fasteners to attach it to whatever other assembly components it needs to. And finally, regarding non-rigid joints, so it is possible to consolidate moving assemblies to flexible single prints. It requires much more careful design, and because of this, it's only worthwhile doing that if you have, if you're planning on producing a high number of them, and if reducing the complexity of your assembly is really worthwhile. So that can really reduce the amount of time it takes to assemble a large number of these components by producing them in their functional form right off the build plate. So there are two primary methods of printing non-rigid joints, and I'm going to switch over to SolidWorks now. So I'll start with the simpler method. This method would take an assembly like this, where you have 5 components. You have these 2 parts, the large parts here, and then you have this green fork or this green pin that moves through the middle of them, and then you pin it at the top here. And so this is 5 pieces that will need to be assembled, printed separately, and then assembled once those prints are complete. And another approach is actually to design them so that you can print these parts as a single piece. And not only will it reduce the number of components that you're using, but you'll be able to print it in its flexible form right off of the build plate. So what I've done that's different from the previous version is that I've made these surfaces here, rather than being all flat on the bottom, they are angled, and this allows them to build without filling the inside with support, which would be challenging to remove. And I've also made both of them land flat on the bottom of the build plate, so that as they print, they don't need to touch each other except at a few places where the support will build under those overhangs here. But that support will be much easier to remove than if you tried to do a similar thing without these self-supporting build angles. So this reduced our assembly from 5 components down to 2 components, and it separated it. It brought it down from 5 components that need to be assembled down to a single component that comes pre-assembled off of the build plate. So the one other thing I wanted to take a look at is another option, which is useful in a very rare number of cases, but if you have one of those cases, it can be very useful, and that is to print a part where it has a small interface between the 2 components that are intended to be flexible, and using our release ink on that interface between the support and the model, you're able to crack this joint and make a moving assembly without both parts needing to be attached to the bottom. So this bottom part will be flat on the bottom and can be fastened to a breadboard or something else, and this top piece will be free to move despite printing them in a single build. And now I just wanted to mention a few things about Rise's process that make it particularly effective for this approach. So if your goal is really to reduce the amount of post-processing involved in creating your assemblies, that can both involve the post-processing involved in putting the parts together, but it can also involve the post-processing involved in preparing parts for assembly after they've finished printing. So because of our release ink technology that makes it easy to remove supports and complete the post-processing of parts, it really reduces the amount of time it takes to get a part from off the printer into its functional form to be actually used on the floor. So there are a lot of things that we've designed into our process to simplify and streamline it. That includes a lot of automation in our software so that you won't have to be an expert and know exactly how to manipulate your parts. A lot of the decisions that need to be made about slicing the part can be done automatically by it, and that reduces the amount of time you need before putting your parts on the printer to process a part in the software, and it also reduces the amount of expertise you need. And then, as I mentioned, the post-processing is as simple as peeling the supports off. There's no soaking, washing, drying, cleaning, or coating required. And this allows you to really get your parts ready to use very quickly. So that's the end of this webinar. That's all that we have for today. Thank you all again for joining us. We're going to put a link to a survey in the chat box. If you have a few minutes, we'd really appreciate if you could fill that out for us. Otherwise, I'm going to be hanging out here for a couple of minutes to answer any questions you have. If you do have questions, please just type them into the chat box, and I will answer them as they come. Other than that, thank you for attending our webinar, and please have a nice day. Okay, so one person asked, what's the size of the build plate? So this would, I expect, refer to the fact that combining too many components together can produce assembly or can produce single build jobs that are larger than the dimensions of your build plate. So the limit of our build plate is approximately 12 inches by 8 inches and 6 inches vertically. We do have methods, if necessary, of producing parts that are larger than this using a chemical called D-limonene. So typically, it's best to reduce the size of your consolidated assemblies so that they'll fit the build plate, but if you have cases where that's not going to work, then there are some methods that can help you out. Another person has asked, can you use inserts for the internal components? So as I mentioned, it's best to design around internal components. It's best to design so that you'll end up with assemblies that you'll still be applying the internal components separately and then fastening them in from the outside. There are some methods that will work in certain cases of applying inserts. I recently did another webinar on metal inserts where I detailed some of those options, and those are available on another webinar that is on our website. All right, it doesn't look like there are any more questions, so we'll wrap this up here. Once again, thank you all for joining us for today's webinar, and please have a nice day.